Hello, astronomy class. You guys have no idea how much I miss being in class with you and how sorry I am that we don't get to spend the rest of the semester together because this was way more fun before it went online. I wanted to talk to you a little bit about the Ages of Star Cluster sheet I had posted. You don't need to do it or turn it in, but I do want you to kind of have an understanding of how we look at star clusters and what we use them for and why. So basically, hopefully you've watched the HR diagram lecture and went through your PowerPoints and you have a good idea that low mass stars live very long lives, medium mass stars, more like the sun, are in the middle of the road, and then very massive stars have short lives. Now, I know on a few of the other lectures I didn't go real in depth between low, medium, and high mass stars. For physical science, a lot of people just break it up into high and low mass star, but it actually is a little more complicated than that. And what a lot of people refer to as a low mass star is actually a medium mass star like our sun. Um, the thing about the lower mass stars is we really don't know what happens to them as they die out because their life expectancy is longer than the age of the universe. So even if a star, a low mass star, was formed at exactly the same time the universe was formed, which it wasn't, that's going to be a later conversation, but let's say it was formed just shortly after the universe was formed, then um, it wouldn't have died yet. It'd only be about halfway through its life, if that, depending on the actual mass. So there are some things out there we really don't know what happens. Oh, apparently I got to scroll. Sorry. Now the only math is this sheet here, and I will post a picture of the key. It's just easier if I work it out with a pen and paper than rather than type the answer in. And basically, if you know the mass of a star, there is a mass luminosity relationship and there is a mass life expectancy relationship. The mass luminosity relationship is very easy. It's however many solar masses to the 3.5 power. So for a star that's zero point 0.4 solar masses, again, we're going to ratio everything and we're going to base it off the sun, you would have 0.4 to the 3.5 power, which gives you a luminosity of about 0.04 times the luminosity of the sun. Life expectancy is this Greek letter tau, but it's 1 over the solar mass to the 2.5 power. So for life expectancy, you would have 1 over 0.4 to the 2.5 power, which would be about 9.88, close to 10. So it would live 10 times as long as the sun. Well, the sun's going to live to be 10 billion years, so this would be a 100 billion year star. So clearly those haven't died out yet. For the 2 solar mass, you just take 2 to the 3.5 power, so it'd be 11.3 times the luminosity of the sun. And then it'd be 1 over 2 to the 2.5 power, so it'd be 0.18 times the lifespan of Mr. Sun, or say zero point 0.2. So 0.2 times 10 billion years, so it only lived to be about 2 billion years old. Again, I'll post a key. The tests are going to be multiple choice. They're not going to be math intensive. Yes, I can hear you cheering from cyberspace, but they're not going to be math intensive. I just decided that was not going to be fair to you, but I do want you to understand those kinds of relationships. All right. I want to come down to these pictures here, and we'll focus on this picture here. So what they do with HR diagrams and star clusters is they will plot all the stars on an HR diagram in a star cluster. And the nice thing about a star cluster is you can assume that they're roughly the same distance away and that they are roughly the same age. Okay, so all these stars formed at the same time, but they are different masses, so some of them burn through their fuel a lot faster. When you look at a star cluster, you study what is called the turnoff point. The turnoff point is going to be this spot right here. I'm going to scroll down to the reference page real quickly. Okay. Now, up here, these are very, very young star clusters. You'll see that some of the higher mass stars have made it onto the main sequence band, but these stars here, these stars are not leaving the main sequence band. These stars are actually protostars. They just haven't quite started fusing hydrogen yet, and so once their core heats up a little more, they will come over to the main sequence band. But because they're lower mass stars, it takes them much longer to get to the main sequence band than it does for a higher mass star. Then you'll come down here and you'll see that those lower mass stars are starting to get on the main sequence band, but at the same time, those very high mass stars are actually leaving. So a high mass star can go through almost its entire life cycle in the time it takes for a low mass star to just go from nebula to the main sequence band. And then you'll see that a few more are starting to come off down here, and then a few more, and then you have a few more, and you're even starting to get some white dwarfs. Basically, for the age of a star cluster, the further down the turnoff point, so on this one, the turnoff point would be here. On this one, the turnoff point would be here. The further down on the band, the turnoff point, the older the star cluster. Now, this is important because by looking at star clusters and ballparking their age, we can kind of figure out how old parts of the galaxy or other galaxies are. There are parts of the Milky Way that are much, much older, like, say, 13 billion years old, versus some younger parts of the Milky Way that are only about 10 billion years old. And the way we know this is through star clusters. Now, down here we have the spectral class O, B, A, F, G, K, M. Remember, Mr. Sun is a G-type star, so this particular star cluster would be about the age of Mr. Sun's life expectancy, or about 10 billion years old. I'm going to pop back up here. Up here, it gives us the spectral classes. It says A and B have core supplies for about 250 million years, 2 billion years, type G 10 billion years, K and M 30 billion and plus years. We really don't know what a 30 billion year old star cluster looks like because we don't have one yet. Okay. I hope everything is going well. This is one of the few astronomy lectures that's just for you guys. If there's any questions, please let me know. Don't hesitate to text me, call me, email me, whatever. As I get things set up, I will continue to post them. Take care.